Hey guys, so in this video we're going to learn about differentiation. Now what do we mean by differentiation? Let's start by looking at an example of a function. Let's say that I have the function f of x is equal to x squared, and we can say y is equal to f of x, and let's look at the graph for y is equal to f of x. So here I have the graph for y is equal to f of x. In other words, I have a parabola here, the curve that has the equation y is equal to x squared. And the question I want to answer here is, what is the slope of the tangent to the curve at the point x comma f of x? What is the slope of the tangent to the curve at the point x comma f of x? So what we're doing here is we're taking a point on the curve that has the x coordinate x, and it has y coordinate y is equal to f of x. So we're taking a random point, a given point on this curve that has the x coordinate x and the y coordinate f of x, and we want to know what is the slope of the tangent to the curve at this point. Now in order to answer this question, let's take another point on this curve, and let's say that this point has the x coordinate x plus h, and therefore the y coordinate over here would be y is equal to f of x plus h. So now we have another point on this curve that has the coordinates x plus h comma f of x plus h. So what we have here is we have these 2 points. We have the point x comma f of x, and we have the point x plus h comma f of x plus h. We have these 2 points, and let's draw a secant line between these 2 points. What is a secant line? A secant line is a line that intersects the curve at 2 or more points. So let's draw a secant line between these 2 points. That is the line that intersects the curve at these 2 points. And the question that I have over here is, what is the slope of the secant line? Well, the slope of the secant line is the change in y divided by the change in x. And here we can take this point as x2 comma y2, and this point over here is x1 comma y1. So we can say over here that the change in y is f of x plus h minus f of x, and the change in x over here is x plus h minus x. So that's equal to h. Now here we can say that the slope is equal to f of x plus h is simply x plus h, the whole thing squared, minus f of x, so that's just x squared, divided by h, and therefore we can say that the slope is x squared plus 2hx plus h squared minus x squared divided by h. And what we see here is we have x squared and negative x squared eliminate each other, and we have 2hx plus h squared in the numerator and h in the denominator, so we can factor out h in the numerator, leaving us with the slope as m is equal to h times 2x plus h divided by h. And here again we have h in the numerator and the denominator, so that leaves us with the slope as 2x plus h. So here we found the slope of the secant line, but our initial question was, what is the slope of the tangent to the curve at the point x comma f of x? Now if we turn our attention to the graph, we can see that h is the horizontal distance between the points x comma f of x and the point x plus h comma f of x plus h. Now what happens to the slope of the secant line as h decreases? What I'm saying is, if the point on the right, as it moves closer to the point on the left, what happens to the slope of the secant line? As the point on the right moves closer to the point on the left, the slope of the line, the secant line connecting these 2 points, approaches the slope of the tangent. What that means over here is, if you look at the horizontal distance between these 2 points, that's delta x, that's h over here, as that gets closer and closer to 0, as it approaches 0, it becomes smaller and smaller. We can see that the slope of the line connecting these 2 points, that's the slope of the secant line, comes closer and closer to the slope of the tangent. It approaches the slope of the tangent as h approaches 0. So here, we know that 2x plus h is the slope of the secant line. We also saw that as h approaches 0, as h gets closer and closer to 0, as this horizontal distance h becomes smaller and smaller, the slope of the secant line approaches the slope of the tangent at the point x comma f of x. So we can say over here that the slope of the tangent is equal to 2x. Now this h approaching 0, this is what is meant by the idea of a limit. Now the formal idea of a limit is not part of our syllabus, but the limit over here simply means that h is getting smaller and smaller, the horizontal distance is getting closer and closer to 0, but it never actually equals 0 because we can't really divide by 0, right? If we divide by 0, we get an undefined value for the slope. What we're saying over here is that since h gets so small, it's so small that we can essentially take it to be 0. We can assume that h is equal to 0. The slope of the secant line, that's 2x plus h, comes closer and closer to 2x. As h gets closer and closer to 0, we can say that 2x plus h comes closer and closer to 2x. And we know that as h gets smaller and smaller, the secant line essentially becomes the tangent to the curve at the point x comma f of x. So what we've done over here is that we found the slope of the tangent to the curve at a given point x comma f of x, and that slope is equal to 2x. This is known as the derivative. Here we use the notation f prime of x to represent the derivative of a function f of x with respect to x. And that is simply equal to the limit as delta x approaches 0 of delta y divided by delta x. Now what that simply means over here is, if you look at our example, delta x was equal to h, and as delta x approaches 0, as h approaches 0 and it's almost equal to 0, we know that the slope delta y over delta x is the slope of the tangent to the curve or the gradient of the curve at a given point x comma f of x. And when delta x is very small, when it's almost equal to 0, we use dx to represent delta x. And since dx, that's h over here, that's very small, we know that dy, delta y is also very, very small. So we use dy to represent delta y. So over here, dy over dx simply means the derivative of y with respect to x. And that again is the slope of the tangent to the curve y is equal to x squared, or the gradient of the curve y is equal to x squared at the point x comma f of x. So for our given example, we can say that the derivative of the function f with respect to x, that is f prime of x, is equal to the dy over dx. Since y is equal to f of x, that's the derivative of y with respect to x, and that is equal to 2x. And here, this 2x represents the slope of the tangent to the curve or the gradient of the curve at a given point x comma f of x. So for example, if x was equal to -2, the slope of the tangent to the curve or the gradient of the curve at x is equal to -2 would be 2 times -2, which is -4. If x was equal to 0, the slope of the tangent, which would be a horizontal line, would be equal to 2 times 0, which is equal to 0. So the gradient of the curve at x is equal to 0 would be equal to 0. And over here, when we say instantaneous rate of change simply means the rate of change at a given instant or a given point. So when we say what is the rate of change of f of x with respect to x at a given point x comma f of x, we're simply talking about, again, the gradient of the curve or the slope of the tangent at that given point. Now the derivative can also be thought of as the limit of the gradients of a set of chords. What that means over here is the following. If you look at this diagram over here, what we can see is that we have a chord that connects the point x comma f of x to this point over here. A chord is simply a line segment that connects 2 points on the curve. And when we say we want the limit of the gradients of a set of chords, what we're simply saying is we want the delta x between these 2 points to get very small. So what that means is we want to find the slope of the tangent to the curve at this point x comma f of x. And if we look at the gradient of the chord that connects these 2 points, if we move this point closer to the point x comma f of x, we see that the gradient of the chord is closer to the gradient of the tangent. We move it even closer, and again the gradient of the chord is even closer to the gradient of the tangent. And when the distance between the 2 points is negligible, when delta x is almost equal to 0, we can say that the gradient of the chord is equal to the gradient of the tangent at the point x comma f of x, or we can say that it is equal to the gradient of the curve at the point x comma f of x. So now let's answer the initial question. What do we mean by differentiation? Well, differentiation can be defined as the process of finding the derivative of a function. So here, for example, if we were to say differentiate f of x with respect to x, that simply means find the derivative of f of x with respect to x. Similarly, if we were to say differentiate y with respect to f of x, that simply means find the derivative of y with respect to x.